for the morning, and that is Anastasis Kratsios, and he is assistant professor at McMaster University in the Department of Math and Stats, and he'll be telling us about exponential expression rates for, you can read the rest of the time. That's
thank you very much for the introduction and the invitation. I'm super excited to be here. And I think the size of the title reflects my excitement about this topic. So this is actually one of a partner talk. The other talk is given by Shuei tomorrow. He'll be dealing with an open loop analog to this. I'll be looking for closed loop thing. I'm going to be looking for good rates. He's going to be looking for generality. So if you want the whole picture, you'll get it over the next 2 days. So this is joint work with a good friend of mine, Takashi Furuya. So he's an inverse problems guy in Japan, and we always meet at weird times because of that. Okay, so long story short, before I start to talk about the problem, I'm just going to make some general comments, even though I think we all know already that FBSDs are important. So let's just start by saying some general remarks. So of course, FBSDs are super interesting to us because they arise naturally in a lot of places, like control problems, games, and because of this, they come up all the time in finance and economics, okay? So the problem with FBSDEs, not the problem with them, but with dealing with them, is one of two things. They're almost never available in closed form. And then numerical schemes for solving FBSDs, which might be more realistic for a given problem, are challenging to say the least, right? So they're long to solve. They don't work in high dimensions, blah, blah, blah. Okay, so that said, what is the state of the art for numerical schemes? And then I'll criticize it. So state of the art, one branch of state of the art is one of these deep learning powered schemes or class of works, which is called like deep BSD solvers. There's a bunch of work by Janssen, Patrick, and a bunch of other people. But the idea is that you take a classical BSD solver, you replace some of the basis regression steps with the deep neural networks, and things work slightly better. But the problem with that is that every time you want to perturb your FBSD, you have to rerun these guys. Okay, and so at a high level, if I change the terminal condition or I change the dynamics of my process, I have to rerun this, right? So if you have a lot of models or you have some kind of uncertainty, you want to understand how the problem changes for each model in your class, this could be a huge runtime, right? So big problem is very slow because they rerun them many times, potentially infeasible. So instead of saying this last line, I snuck in this slide in the morning. So just to give an idea, okay? So X is giving me my forward process. I'm not going to talk about what it is right now. T is some future time horizon. And imagine I have this infinite family of like BSDs, or FESDs on itself. I'm just going to look at the backwards process. So these are indexed by my terminal condition, which is basically indexed by some C1 ball. Okay, so that's a big set. So of course, it's obviously infeasible to solve all of these simultaneously, which is actually what I want to do. Yes.
Alpha is fixed. Right?
Yes. Alpha is all the notation that I just like glossed over is TBD in like 2 slides. Yeah, alpha is fixed and T is fixed, X fixed, and Y and G are like yes.
That's the actual plus.
Yeah. That's an extra plus just to keep you on the toes. Thank you very much. Cool. Okay, so that's it. But we have an infinite set of these. Okay, I'd like to solve them simultaneously. This is the point of the talk. Of course, this is infeasible by rerunning this many times. So what if I just make do and say I want to solve a really good finite subset? But what I mean by this is say you pick some delta, Barzella, Scully, we know this guy is compact in the supremum norm. And so I just take a finite collection of these, And so in that case, you can just rerun your deep BSD solver once for each like FBSD that corresponds to one of these GNs in my delta net of my C1 ball. Okay. Now, to really drive the last point home on the last slide, why is this completely wildly infeasible? Well, the question is how big is n? In other words, how many of these BSDs do I have to solve, FBSDs? Well, a lower bound is double exponential in delta in the dimension. So like in the reciprocal sides of the net. So in other words, even if your solver takes a second to solve, you'll be here till like the world loses heat. So it's impossible. So this is not to say that the problem is impossible, but the approach is impossible. So yeah, no way. So this is the goal of my talk. So I'm going to do like a funny structure for the talk. I'll start with the goal. I'll start with a high-level theorem, and I'll break it down for the rest of the time. So the objective is, yeah, to solve FBSDEs with random terminal time, families of them. And my inputs are going to be the following. The inputs are going to be a terminal condition and dynamics of the backwards process. That's what I get. My model gets that as an input. My model, let's say it's pre-trained. My output to my model is going to be automatically gives me the solution to the corresponding FBSD. So what I mean by this, I'm not going to rerun some solver. The model just takes this function, like takes the input data and the dynamics, and automatically gives me an answer, right? And that's the key point. I don't want any retraining. So there should be an automatic solution for each input. Okay. So let's now kind of give a high-level idea of the setting. I'm going to gloss over some technical details because that's not fun. So my forward processes are going to be simple, but actually these are kind of already hard. They're going to be in high dimensions, so it's D at least 3. You can make it whatever you want, just at least 3 for some technical reason. It's just going to be some Brownian motion with some kind of correlation. Gamma is it's a positive definite matrix. Okay, that's my forward process. There's one forward process for all my problems. Okay. These are going to evolve inside some domain D in RD. And this domain is bounded with C1 boundary. Okay. And tau is going to be the random time where this whole show stops. And it's the first time where my forward processes X from this domain. Okay. And for each, so now I'm going to consider the following family of FBSDs, which looks like this. So to answer that questions, this explains the plus. Yeah, so I'm going to be given so a coupled system. Here are my forward dynamics. Alpha is given, and what isn't given, and like so this creates indexing my family, is two things: a perturbation to the terminal condition, which is the following form. It's just like some boundary, so some function evaluate my forward process at the time which I exit the domain, and some additive perturbation of the dynamics of the backwards process, given but just additively by some function of the forward process. Okay, so in other words, for every G and for every F0, I have some FBSD, same forward process, same terminal time, same domain. Yeah, but I have infinitely many backwards processes, and I want to solve them all in one shot. Okay, so how do we do this? Okay, so is the setup okay for everybody? So I'm so used to teaching, I keep asking that. Okay, so slightly formally, not too formally, the object I'm interested in is approximating the solution operator to this problem. So what that looks like is, oops, how do you go? Top. This is the pointer? Oh, cool. Oh, man, it's as unstable as me. Okay, so basically, oh wait, I have to point it there. Okay, good. Okay, so 6 seconds. So what it takes is, again, boundary data, so G, this terminal condition, some source data, so some perturbation to my dynamics. These will live in some sublove spaces. Okay, I'm just gonna point them with my hand. And it gives you the solution to the FBSD, which is, again, a pair of Y and the Z, so martingale part and the backwards process. Oh, thanks. I wish I was taller, but okay, cool. Thanks. Okay, so again, so the solution operator, all it does, it just it's a fictitious, it's a theoretical object, right? So it gives you a terminal condition, perturbation to the dynamics, and you get the solution to the FBSD out. And I'd like to actually represent this thing, and how? Okay, here's the semi-cool part, using some infinite dimensional deep learning models. So it's good that we had some infinite dimensional talk so far. But so far, I'll say that the fact that we can do this is perhaps not surprising, right? So no surprises here. I mean, there's a massive amount of literature in the last few years on deep learning in infinite dimensions. And there's actually two schools who are really interested in this. There's actually our community and there's the PDEs community, okay? So there's a bunch of results out there. There's also Yosef, Krista, me, a bunch of people over the years. And so there are universal approximation theorems that can say that you can approximate such an operator. Okay, so of course, as usual, this talk doesn't end here. So what's the issue? The issue is that if you want to tackle this problem by universality, and sometimes that might be appropriate, it will be appropriate in Chouet's case. In this case, it's not necessarily appropriate. The reason is because a universal approximation theorem, well, what is it really saying? It says that if you have some function you're interested in, say the solution operator here, and you know that belongs to some broader class of functions, and there is a neural network or deep learning model, whatever, that can approximate this thing. but the complexity of the network corresponds to the worst possible function in that class. It's possible that the functions in this class, imagine this is like some Lipschitz operator or something. Imagine the functions in that class can be highly irregular, much worse structured than this guy. So in this case, the problem that I pose on the board, and this is why it's fundamentally different from the talk you'll see later, is rather well structured. And so even though there exists a deep learning model that can approximate this thing, the parametric estimates are going to be astronomical because they're corresponding to the worst possible Lipschitz function between these spaces. And that's just crazy, you know? So the key point here is I want to have good rates. And so now the true heart of the problem starts. Right? And the point is, I'm not going to go via universal approximation. I'm going to have to approximate this guy from scratch by really understanding the problem itself. Okay? So I'm going to do the talk backwards. This is the first time I try this. I think it makes a lot of sense, though. Let's pose this informally the theorem. The soon to be on archive paper has the formal thing. Okay, so I'm going to look for a solution operator. For me, hats are things that are approximators. So gamma hat, approximate solution operator gamma star. Takashi chose a star. I don't know why. So what that does, again, it takes boundary data, so G, thermal condition, some source data, so F0, the perturbation to the dynamics, and it gives me some other, so it gives me a candidate for the solution of my FBSD, so Y and a Z. Okay, and the idea is that for every approximation error, and for a broad set of G and F, and for every time horizon T, I can get this uniform approximation error uniformly over all the F and G and F. Okay, oh, I flipped the order. So what that means explicitly means that once I have this gamma hats, then all I need to do is plug in F0 and G, and I'll automatically have a good solution to my FBSD. So this is the high level thing. So far, I could have gotten this from universal approximation. But here's the key point. The main point, which I actually really do think is really cool, is that the parametric complexity of this object is surprisingly low, right? So for everyone who's seen the deep learning model, there's essentially 2 or 3 parameters. If your infinite dimensions is 3, one is the depth. So the depth of my model, so if I want an epsilon good approximation error, it's logarithmic in the reciprocal approximation error. So that converges exponentially fast. Wow. The width is actually constant in epsilon, which is extremely impressive too. I'm literally impressed every time I see it. I can't believe that's possible, but it is. And then the rank, which is sort of the latent dimension of this thing, is linear in the reciprocal approximation error. So long story short, the number of parameters is just over quadratic in the reciprocal approximation error. That's really low, okay? Now, to understand how low that is, I'm going to juxtapose that with the recent result of a friend of mine, Samuel Landthaler. He's at Caltech, and soon he'll be somewhere nice, like permanently. I won't say it until it's official. Here is a lower bound in the general setting. So we'll say what's possible in the universal approximation theorem, and you'll see how much of an improvement this is over the worst case scenario. So F and Y are nice infinite dimensional Banach spaces. For example, take separable Hilbert spaces like in Dennis' talk. And F is a Lipschitz nonlinear operator between these things. Then how much parameters you need to approximate this to epsilon goodness. Epsilon goodness, I mean, for this statement to hold, if you want your universality. Again, that's exponential in the reciprocal approximation error. Okay. Now, to understand how bad that is and how much better this is, let's actually take the next closest thing. So there's a result by a magnificent mathematician, Dmitry Yurovsky, or maybe a computer scientist from 2017. Let's understand what this looks like, not in the infinite dimensional case, in the finite dimensional case, and then let's juxtapose everything. So if you have a function that's Lipschitz between RD and R, and you want to approximate it on some compact full dimension, then if you want epsilon good approximation, so uniform, then you need so you need a polynomial number of parameters that's whose degree is equal to the dimension of the space. Yes. So this is the so-called curse of dimensionality. Okay. So that's what breaks down all your algorithms. In infinite dimensions, it's not even polynomial, it's exponential. And actually, I'm claiming to you that I can do it quadratically. And many of my parameters even converge constantly or exponentially. That's really, really a massive improvement. So how is that possible, right? So here's the rest of the talk. So phase 2, this is the theorem. Why should you believe me? Let's explain how this strategy works. So this is a new proof technique that's inspired by some results by Schwab, but we really took it to the next level, and we'll have some sequence of papers coming out soon. So here's the idea. So the idea is it starts from not thinking about the BSD, but rather going to the PD, right? So there's the results by Pardue in like right before 2000, right before Y2K, that says that for every such FBSD, right, like in the previous form, this is why I particularly chose this setup. You can write y and z as some function and its gradient evaluated at the forward process, where that mathematical function solves this elliptic problem. So what I want to be doing is not approximating the solution operator to the FBSD, but rather just approximate the solution operator to this elliptic problem. And what that means is that you give me boundary data, just like I keep calling it that, source data, so I calling this additive perturbation terminal time, and the solution operator to the elliptic problem will give you back this u, or approximation of it, and I just plug in x and voila, and its gradient. Yeah. So this is what how gamma is going to work, and I'm going to go into this into more detail to understand why this is happening. So gamma plus, Takashi chose this notation. I let him. So it's just a solution operator to the PDE. So right, so that takes the boundary data and the source data and gives me the solution operator u to the elliptic PDE, which when I plug in x into u and its gradient, I get the solution operator to FBSD. I get the solution to FBSD for that particular g and that particular F0. Okay, and yeah, this is what it does. So here's the whole pipeline. So you give me an F and a G. I give you an approx. Again, hats are approximation things. So I solve the solution operator to this elliptic problem approximately, and I get some u hat and some approximate of the gradient, and I just plug in x, and that gives me an approximate solution to my FBSD, right? Okay. So how are these rates possible, right? Exactly. How is it? So in other words, I've transferred the question to ask myself, how is it possible to efficiently approximate with the same rates the solution operator to this elliptic problem, right? So to understand that, we need to start actually going into the elliptic problem, okay? So one way to solve it, so let's just fix a g and fix an F0, understand that one case at a time. You can obtain the solution for reasonable g and f, 0, by iterating the following operator onto itself. So you can get it as a fixed point, right? And what is this operator? This is some nonlinear, non-local operator. It looks like this. There's some components. Let me use a Sebastian stick. Okay, so this guy solves the following elliptic problem. Okay, and okay, that's not really that crazy, but here's the really beautiful part. So this guy is the Green's function associated to my elliptic operator, right? Or yeah, without the F0. Okay, so the idea is going to be I want to, using very few layers of my neural operator, it's my infinite dimensional neural network, encode this as best as I can. So imagine that's one layer, and then the depth of my network is going to exactly what it's going to do is it's going to iterate this operator onto itself. So in other words, my neural network model is going to be literally approximately implementing a fixed point iteration, and that's where the exponential rates are going to come from. So the main challenge is not really getting the WG. That's easy to do. It's going to be the Green's function. Okay, so how do I encode this into my network? Right. So in other words, I forgot to say this. My objective is to come up with a neural network that is built around the structure of my elliptic problem, so that those rates are possible. Okay. So let's understand the Green's function to the elliptic problem. So the Green's function has, in this case, has the following beautiful decomposition. So this dates back to the late 70s, effectively 80s. And just from this year, we got the last piece of the puzzle. This is very convenient. So the objective is going to be, notice that the Green's function does not depend on G or an F0. So I need to be able to encode this thing directly into the layers of my neural network. So then when I make this iteration, yeah, it can converge to a fixed point. So I need to understand the Green's function. So there's two parts. The smooth part, and because this does not depend on the input data, G and F0, I can approximate this very easily using some classical neural network theory. So smooth function is easy to approximate. That C gamma is not a problem. The main problem is that the Green's function is singular. It has a big spike. Now, it's not very surprising to imagine that a function with a massive spike has such low regularity around the spike that it is impossible to approximate, right? But here is like the magic. Actually, it has a very, very simple closed one, right? This is just the following thing. So I put some constants and blah, 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 but it's effectively the root of gamma, which makes sense, the positive definite matrix, times some power of the norm. Right? So that's something you can code in like half a line, you know? don't need to like zoom out in your screen. Okay. So the idea is now the following thing: is I can hard code the singular part as part of one convolution against one singular part as one of the layers of my neural operator. This thing I can absorb in the classical neural operator into layers, and I'm actually gonna, by doing that, I'll get my rate. So the idea is basically this: I come up with a layer of my neural operator. So neural operator just means infinite dimensional neural network, which just sounds cooler. Right, gamma hat that approximates one of this, the t that gives, that when iterated gives me a solution to the PD. And then, yeah, and then depth is just iteration. So I just create depth by literally putting the same operator, the same layer into itself. So if I did many times, then I approximately have implemented a fixed point iteration, and this should give me a solution to my PD, and efficiently, because as we all know, fixed point iterations converge very fast. So now in the last few moments, I'll just write down, so the talk is completely structured backwards on purpose. I'm gonna now just define to you the neural operator, because now you see why it works. So let's see what it's built, how it's built. So I abridged notation. This thing makes sense in more general setting. So imagine you have a bunch of functions from some sublevel spaces that are going in, and some bunch of functions of some sublevel space are going out. So yeah, so what it does is you take the V0, it's just supposed to be like a G and F0, okay? And in this case, okay, the notation is terrible on the first line. Yeah. Oh my God. Okay, so that should be like L1 times L1. Yeah, so then you just get some other function out which you evaluate at X and its gradient, and that will be the solution. Approximately. So what does it look like? So what you do is, well, you get the function comes in, or the pair of function comes in, and you do the following operations iteratively, right? So first, you do some component-wise multiplication via some matrix. So it's like a classical neural network in finite dimensions. You do some specific convolution, which I explain on the next slide. And you do some other kind of convolution, which I do on the next slide. Long story short, this is like the smooth part of the Green's function, convolving and this is like the singular part, okay? And then you add some additive functions, like an infinite dimensional bias. That's just a classical neural network. This doesn't matter, whatever. After you do that, you apply component-wise nonlinearity, just like in the finite dimensional case. And specifically, you're going to be choosing the square of the ReLU function for a highly technical reason. So this is how it's called ReQ. That's what sigma is, and the black dot means component-wise composition. Okay, you do this again and again and again. This is the depth. The number of times you do this is the layers. And at the last layer, you did it one last time, but without adding the component-wise composition. So it's like a really direct analog of the finite dimensional neural network, except there's these convolution operations at each layer. Now, what are these convolution operations? They're just very straightforward. What they are, the singular part is exactly this. Since we have, I have my height booster. So since you have access to the closed form expression for the singular part of the Green's function, I literally just convolve this, do some matrix multiplication at the end. And the smooth part, I approximately implement this. And how to do that is kind of obvious. Maybe not just it. I think it's straightforward. It's just the following thing. You do some kind of expansion via some de Brochury's wavelets in my sublevel space, which are optimal. Okay, and that's it. So when you constructed that, so that's the model that gave the efficient approximation rates, which were impossible via a universal approximation theorem. And summary, this construction is, I think, pretty cool. It avoids terrible rates by directly encoding the PV structure into the neural network. Okay, and the depth of my neural network has a very concrete meaning. Everyone's always saying, what are neural networks doing? I'll tell you in this case, the depth is encoding iterates of fixed point contraction operator T. I took away the gamma to make it more beautiful. So in conclusion, what have I talked to you guys in this talk? Right. So with this technology, you can now simultaneously solve infinitely many FBSDEs in one shot, which is, of course, completely infeasible, even by really fast algorithms before. Okay? You need roughly reciprocal quadratic number of parameters in the approximation error to do it. That's pretty impressive. That's not even possible typically in finite dimensions, unless you're in 2 dimensions, or 1 maybe, I guess. Okay. And unlike classical deep BESD or FBSD solvers, we don't have to re-optimize in each time. You optimize once, and you can keep plugging in and play. And unlike neural operators, so these are infinite dimensional neural networks, they have a cool name. We don't need a wildly infeasible number of parameters. We have a very grounded number of parameters, at least in order. I can't promise the constants. You know? Okay, and that's it.
Okay, open the floor to some questions.
Okay.